we are talking rotational and linear quantities and the relationship between them. So, we've already discussed in this chapter the idea of angular position, angular velocity, and angular acceleration. And we want to relate those back to linear quantities. So we want to think about, say, the arc length, the distance that you travel as you rotate through some angle. The tangential velocity, which we normally just think of as the velocity, because it really is, unless there happens to be a radial component of the velocity as well. When it comes to the alpha, we do have the tangential acceleration, and while we're talking about it here, we will mention again the radial acceleration and how that relates to the rotational quantities. You've seen it before, but we'll talk about it again. All right, so first things first, if we're thinking about an XY coordinate system and we're thinking about something that is a distance r away from the center and at an angle, we can actually define how far that has gone. It is what we would call arc length s. So we know the distance to go around a circle. The circumference of a circle is 2 pi r, for instance. And we can actually think about how that would relate to portions of going around a circle. So for instance, in terms of radians, the radians that we've traveled divided by 2 pi will be equal to the distance that we've traveled, the arc length, and the 2 pi r. So by thinking about what fraction of a whole angle, we can actually figure out what that arc length should be. And the first thing you should notice about this is, if we just wanted to find out how s is related to theta, the 2 pi cancels, and we can just say that the arc length is r times theta. And indeed, that is exactly what we are after here. The linear distance traveled as you rotate through an angle theta would be r times theta. It's usually more proper for us to think about it as a delta s is r delta theta. So we think about how far we've rotated in terms of angle and the radius, and we can turn that into a distance. You will sometimes find this also written as just an x, a distance. This is usually used when you have something like cable wound around something and the cable's unwinding or winding up, because the linear distance traveled by the cable and the amount of distance along the arc will end up being the same thing. It is also used, and we'll see this in the next chapter, when you have something rolling without slipping, to find the distance that it would roll along the surface. So the whole proper thing would look like that. All right. Well, this s is a real distance. So if we want to think about the tangential velocity, how fast it is traveling to the side, we can think about what's going on with delta s divided by delta t. And of course, that's going to look like r delta theta divided by delta t, but we know delta theta delta t, that is omega. So we very quickly recover this idea that r times omega will give us the tangential velocity, and that would be the speed you'd be traveling along here. Okay. Notice that it does depend on the radius you are at, so while a solid object will rotate uniformly, every piece of it rotates one cycle in the same amount of time. The actual speed depends on where you are inside of it. The further you are from the center, the faster you have to go to complete the turn in the expected time. So that gives us the second of these. Okay. Well, if the tangential velocity is changing, then we can find the tangential acceleration. It would just be the change in the tangential velocity divided by the time, which would just be r omega over delta t, and, well, technically delta omega over delta t, because we'd have a change. And that is just r times alpha. Okay. And for the moment, submitted without proof is just that we can write the radial acceleration So the tangential acceleration would be telling us about how you are speeding up or slowing down as you go around here. And it does depend on the alpha, but there's also potentially, or if you're following a circular trajectory, there is always a radial component. And of course, the Pasadena textbook considers the radial component to be the opposite in sign of the centripetal, that our book considers them to be the same. So here we would just say this is omega squared times r. Or if you prefer, it would be the tangential speed divided by r. Sorry, tangential speed squared divided by r. If you square out r squared omega squared divided by r, you get r omega squared. It ends up being the same thing. Okay. So those are the things you must remember in order to convert back and forth between rotational and linear quantities. All right, that's it for this one. We'll be doing kinetic energy of rotation next.